New research is reshaping the way we understand carbon storage on land, revealing that most of the carbon sequestered in terrestrial ecosystems is not stored in forests, as previously believed, but in soil, wetlands, and bodies of water. This discovery, which highlights the crucial role of non-living carbon pools, is a significant step forward in climate science, offering new opportunities for enhancing carbon sequestration and mitigating human-caused emissions. Scientists have long known that terrestrial ecosystems absorb a substantial amount of carbon dioxide, helping to offset about 30% of emissions from human activities. However, much of the focus has traditionally been on forests, given their well-documented ability to capture carbon through photosynthesis. While trees play a vital role, this new study, published in Science, demonstrates that forests account for only a small portion, about 6%, of the total carbon gains observed over recent decades. Instead, most of the carbon is being stored in non-living pools, such as soil organic matter, lake and river sediments, wetlands, and even human-made reservoirs. By analyzing data from 1992 to 2019, researchers found that the amount of carbon stored on Earth's surface has grown significantly, with an increase of about 35 gigatons. The rate of terrestrial carbon sequestration has risen by 30% in the last decade alone, from 0.5 gigatons per year to 1.7 gigatons per year. This is a promising trend, suggesting that land-based carbon sinks are becoming more effective at absorbing atmospheric CO2. Importantly, a substantial portion of this carbon is stored in environments where it remains trapped for long periods, making it less susceptible to rapid release. Unlike forests, which can become vulnerable to climate-related disturbances such as wildfires and deforestation, these non-living carbon pools provide more stable and enduring storage. One of the study's most intriguing findings is the extent to which human activities contribute to carbon sequestration in ways that were previously overlooked. For instance, the construction of dams and artificial ponds has created new environments where organic carbon accumulates under low oxygen conditions, reducing its likelihood of re-entering the atmosphere. Even timber, when used in long-lasting structures, represents a form of carbon storage that can persist for decades or even centuries. These insights challenge conventional wisdom and open up new possibilities for designing more effective carbon management strategies. Current global vegetation models have historically overestimated the role of forests in carbon sequestration while underestimating the contributions of soils, wetlands, and aquatic environments. By providing a clearer picture of where and how carbon is stored, this research can help refine these models, making them more accurate and useful for climate policy. It also highlights the need to protect and restore not just forests, but also other critical carbon sinks, such as wetlands, peatlands, and agricultural soils. Overall, this study offers a hopeful perspective on the planet's ability to absorb carbon, while also emphasizing the importance of maintaining and enhancing these natural processes. As scientists and policymakers continue to explore ways to combat climate change, recognizing the hidden power of soil and water as carbon sinks may prove to be one of the most valuable insights yet.